Okay, so our speaker today is Avinash Yadav, and he will talk about discovering symmetry invariants and conserved quantities by interpreting CMS neural network. I don't know what that is, but you'll probably explain.
Uh, Hello everyone, I am Avinash, and as Sir said, I am today going to present this paper. Uh, it is no doubt that, of course, neural networks can be applied in the area of physics, but a deeper question is whether they can actually learn the physics or not. What this paper tries to address is how what the neural networks actually learn. The paper tries to interpret what the neural networks have learned actually, and then it shows that indeed the neural networks are able to learn the physics. They are like able to find the invariants and conserved quantities, and thus we can say that okay, neural networks can actually learn physics. So
Well, not
this
necessarily physics, right? So if you can learn some conserved quantities or symmetries in your data set, which may have nothing to do with physics, it's still useful property, right?
yeah.
Go ahead. Sorry.
Okay, yeah. So the what this paper mainly contributes. So SNS actually stand for Siamese Neural Networks. So it demonstrates the use of Siamese neural networks in context of special relativity, electromagnetism, and motion of particles in central potential. So these SNNs basically, for each of the cases, these SNNs learn different physical phenomena, but all the phenomena are basically like this. They are related by an equivalence relation, like Lorentz transform, etc. So basically, and then after training these SNNs, they interpret the intermediate. Basically, they interpret what the SNNs have actually learned, and then we actually find out that they learn the physically conserved quantities and invariants like space time interval or angular momentum. So coming to Siamese neural networks, what Siamese neural networks basically are, they are like simple neural networks, but so you have basically two inputs and two neural networks. It is not necessary that they have to be convolutional networks here. They can be anything, but their weights are shared. That is, their weights are same and they are updated simultaneously, and they are used to encode these two inputs, and then basically we compute by some formula, not necessarily Euclidean distance, but by some formula the similarity or the distance between them, and basically then we pass it through a function like sigmoid to compute their similarity. So these are basic. So this was the Siamese neural network. This is the neural architecture used in this paper. So what they have done is basically they have taken the classical Siamese neural networks and added a bottleneck layer here so that the outputs of this layer can be observed. The bottleneck layer has basically only one neuron, like there is only one neuron there for each of the networks, so that like interpretation can be easy. We can increase number of neurons, but then interpreting them will become harder, but we will get more accuracy. And we will come to the algebra layer and later. So basically the input data is in form of pair of samples xi, which are each of the input data has two values, xi and xi prime, and they are basically related by an equivalence relation, and the output label y equals to 0 is associated with the pairs that correspond to the same class. That is, if xi and xi prime are related, then there is an output label which tells that okay, they that okay, they belongs to the same class. And if xi and xi prime are not related, the output label is 1. And the output of the Siamese neural network is the probability that signifies whether the two samples belong to the same class or not. So yeah, coming to this, the output of the bottleneck layer, this one is the intermediate output. It is termed as the intermediate output of the SNN. The intermediate output, that is output of this layer, is merged by this algebra layer together. So what this algebra layer does is basically f of xi is the output layer of the first network, f of xi prime is the output of the second layer, and basically it computes the difference square and then passes through a so and basically multiplies it with a weight w and adds a bias and passes it through a sigmoid, so that we can get a probability that how similar these two inputs are, or how similar or how dissimilar they are. And so for
Is the
training,
W and B trained as well here or no?
yeah,
W.
they are trained. Yeah, they are trained actually, I guess.
And what about the actual network? It's also being trained, right? So
Yeah. Basically, the whole network is trained, and the weights of these two are updated simultaneously.
simultaneously, sure. Yeah.
Yeah. Okay. And for training, we use the binary cross entropy loss function, which is I guess, a standard loss function. And I, okay, I think okay. So if the output label is 1, then this term will be 0, and then the loss will be basically minus log of p of yi. So if the probability is close to 1, then it will be close to 0, so the network will be penalized less. But if it is like much lesser than 1, then it will be penalized more. And same case goes for, and similar goes for when the output of the network is 0. Like if the like if the yi is actually 0, the original label is actually 0. So now let's come to special relativity. So what happens in special relativity is basically, if there are two observers traveling with respect to each other, that is like they have they have different velocities, they have different frame of references, then if an event is happening, they will it is possible that they will, if an event happens at xyz coordinate and a time t, then it is possible that they will observe, one observer will observe that event at a at a different coordinate and at a different time, and another observer will observe that event at different coordinate and uh, different time. So an event is basically defined as an 4 vector that is x, y, z, and time also incorporated into it. And the space time interval s is defined as this is basically inner product of two 4 vectors, and it is defined as minus t square plus x square plus y square plus z square. And there is basically the Lorentz group. So Lorentz group is set of transformations which preserve the scalar product. That is, if like we transform the 4 vector using a Lorentz transformation, then this quantity will not change. We can see it as a rotation of the vector. Like this, we can see it as a length of the vector, and we can see the Lorentz transformation as some rotation in this 4-dimensional space. So basically, the length is conserved. What they did was, there are basically two observers whose positions are same, but they are moving with a relative velocity in some direction. And then a training data set consisting of pairs of measurements of same events are created. So basically, we have a set of Lorentz transformations, and we take a coordinate, we generate a coordinate t, x, y, z, and then using that Lorentz transformation, we generate another coordinate t prime, x prime, y prime, or z prime. And then the label associated with these two will be 0, because these are actually related by the Lorentz transformation, and this is basically, and this is termed as the positive data set. And the other part, which is the negative data set, is basically created by after creating a positive data set, these second coordinates are basically permuted randomly, so that here some other coordinates will come, and these two will not be related by a Lorentz transformation. And after that, they train the network, and after training, the so it they assume that the Taylor expansion of the decision function is sufficiently accurate at the decision boundary, and we can approximate it by a polynomial. And then the outputs the output of the intermediate layer, that is the bottleneck layer. So we perform regression on that to find out what the neural network has basically learned. So first we try polynomials of degree 1, and after that we see that okay, the results are not so much satisfactory. Then polynomials of degree 2 are tried, and so the result of the regression is basically and then we find out that, oh, the polynomial of degree 2 are basically are a good fit. And after the basically the output of the intermediate layer f of x, and the input of the four coordinates x, y, z, and t, the relation between them comes like this. And we can see like there are some terms which are dominating, like t square, uh, x square, y square, z square, and rest others can be treated as a constant basically. So what the network has done is uh, the output. So the output of the intermediate layer is basically dependent on on the space-time interval, which which is basically the conserved quantities, and it depends on nothing else. So we can say that okay, our network has learned this quantity. It has learned to find out this quantity, and thus we can say that okay, it has learned the physics. This might be a doubtful statement, but okay. And this is the correlation graph. So we can say that the intermediate output and the S square are strongly correlated. There is a strong positive correlation between them.
It's learned the invariant, right? So it didn't learn physics. It's learned that there's something.
Yeah, there is something
which is
that is
invariant
invariant.
between the two samples. They're basically the same. Okay.
Yeah.
It's
So
interesting that t squared it learned not as good, well, slightly not as good as x squared, y squared, and z squared.
yeah, the coefficient is like it's
A little
slightly
bit
smaller, with
right.
which
Okay,
can
but the others are other coefficients are way smaller, so it's
yeah. So it basically learned this invariant,
yeah.
And then what they did more was basically they tried to form a data set with keeping this as constant. So basically all the inputs, they have the same like all the inputs will had same space-time interval. And after that they tried to find out that what the neural network will learn now, and basically they got very poor results. So the paper concluded that okay, there are no other like conserved there are no other invariants which the neural networks can learn, but there is an open end to this, like the neural network might not be strong enough to find out some other invariant. So
But there were
now,
no other invariants in that case. If you just
yeah, there were no other invariants in
so
this
there's
case.
nothing to train it on. You just keep something fixed, right? And
Yeah. So basically, they tried to find out that is it possible that there exists some other invariant,
yeah.
like some, yeah. And now coming to the particle in a central potential. So basically, the second system under consideration is a particle in a central potential, such as a planet moving in the gravitational potential of a star. So Newtonian gravity can be formulated via this Hamiltonian, which and this Hamiltonian is basic. This you can relate the Hamiltonians with the total energy of the particle. So basically, we can, if we know the initial position x and the velocity, initial velocity v of the particle, then we can calculate its trajectory by the Hamiltonian equation of motion. That is x dot equals to del h upon del px and rest of these equations. So in such scenario, basically the angular momentum and total energy are conserved actually. So what the so upon performing the regression, upon training the neural network and performing the regression, we see that the neural network actually learns this the output of the intermediate layer is basically dependent on the uh, angular momentum of the particle. That is Lg, which is a conserved quantity in this case. And basically, there is and basically if after that, if we keep the angular momentum fixed and produce another data set such that angular momentum is same for all of them, all of those objects which are simulated to find out the velocity and position, we find that the polynomial regression actually fails because and it basically fails. And after like if we compare the intermediate output of the remaining invariants, we found out that the output is actually strongly correlated with the energy of the system. To circumvent this problem, another term 1 by r is included. Another term 1 by r is included in. So basically, initially the input was x, y, vx, and vy. So the initial position and the initial velocity of the particle. Now 1 by r is also included in it. So 1 by r is basically under root x square plus y square. That is the distance from the like the source of the potential. Like if the it is distance from the origin. Basically, you can say if the origin is at the center of the star around which the planet is moving, then this will be the distance from uh, the star. So we found out that after performing the regression, we found out that basically it learns some constant plus and angular momentum, which was actually constant in this scenario. It was kept constant plus this total this term, which can be basically related with energy. There is an vx square term, vy square term, and 1 by r. So it can be related to energy. So we can say that okay, our system learned that if we kept the total angular momentum constant, our system learned that the total energy is also constant. So it found out that there is another invariant here. And this
But since the sorry, since the
yeah,
angular momentum was constant, I don't understand why it just doesn't appear as a constant in this equation.
uh,
I mean,
yeah,
I understand that at the end you just do the fitting of this
yeah. They
this
actually fit.
function,
Yeah.
but like changing this to a constant would just give you as good accuracy as anything else, right? So you can basically shift your term from the second term to the first, and vice versa, because it is a constant, right? In this setup.
Yeah.
Okay, good, thanks.
Uh, okay, so basically these are the co correlation with the energy and the intermediate output when angular momentum is kept constant. So if angular momentum is kept constant, we can see that energy and intermediate output are highly correlated. And if and when angular momentum is not kept constant, the correlation plot between energy and intermediate output comes like this. So there is not much correlation, and the correlation plot between angular momentum and intermediate output comes like so they are basically, there is a negative correlation between angular momentum and intermediate output. Now coming to the last part, which is the electromagnetism. So electric field.
Sorry, I need so in the previous so the reason why you couldn't see can you go to the previous slide?
Yeah, okay. In just a second.
So on the right, the reason you couldn't see correlation between energy and the output is not because they were not they couldn't be there. It's just because they were not discovered, and somehow it's easier to discover the angular momentum invariant other than energy invariant. And maybe if you had like two output neurons, then both would have been.
Then it might have been easier to find out the correlation.
Right. So it just tells you that it's easier to figure out that there is.
But actually that will then make the regression tougher, I guess. So
right.
There is something like a trade-off.
Yeah. Okay. Good. Thanks.
Yeah. So now coming to electromagnetism. So basically the electric and magnetic field, and in this we consider the behavior of electric field and magnetic field under Lorentz transformation. They basically, so we incorporate the electric and magnetic field into the electromagnetic field strength tensor, and the Lorentz transformation of this tensor is defined as following. And there are two invariants in this, which is the which is that the b determinant of f is basically dot product of b vector and e vector, and the modulus of b square minus e square is also a conserved quantities. So we basically again similarly form a data set and train it, and then after performing a polynomial regression, we found out that okay, the intermediate layer is dependent on this the intermediate layer is dependent upon the E dot B, which is the conserved quantity. And again, after like keeping this as constant, if we kept this as constant, so after that, performing a regression again, we found out that okay, the regression now depend on mod of E square minus modulus of B square, which is the second invariant quantity. And these are basically the correlation plot. So when E dot B is not kept as constant, then we can see that it's harder to find the as said, it's harder to find the correlation between the intermediate output and modulus of E square minus modulus of B square. But when it is kept constant, that is E dot B is kept constant, a clear correlation between these two can be observed. That's all, I guess.
Perfect. Thank you, Avinash. Question? Well, maybe there'll be questions and you have to share your slide again. But
okay.
Well, let's see if there are any questions. All right. Looks like I asked all the questions. All right. Yeah, that was great. I think this is a great idea to do and to try to learn what the invariants are. Should be very useful. Thank you, Avinash, and I'll stop recording now.